Okay, welcome back. So let's have our last talk for today. We have Dr. Pritam Ghosh from Ashoka University.
Thank you. Thank you for having me here and giving me this opportunity and organizing this nice workshop and conference. So today I'll be talking about something about the geometry of free groups, extensions. Right. So what is the setup that we have here? We'll consider a short exact sequence. So Q is a subgroup of out F, finitely generated. And you want to ask the question that what conditions we can put on Q so that EQ is hyperbolic or relatively hyperbolic. We focus on two cases. In particular, when Q is cyclic and Q is F2. Right? So in the cyclic case, it is a well-known result that in both these cases what happens, okay, so why are we choosing these two? So what happens is in this case, EQ will be actually have a semi-direct product structure. Okay, so these things are in some ways easier to understand than arbitrary extensions. So our focus will be here. So one of the well-known results is that this is due to Brinkman. That F is hyperbolic if and only if is atoroidal. Atoroidal meaning, if you have been in Daman's lectures, so this means no periodic conjugacy classes. Of course, so we want to extend this result and try to see, the hyperbolicity, what about relative hyperbolicity? And that's one of the main focus today. So what condition do we put on phi so that this extension group is relatively hyperbolic? Okay. All right. So the goal here is to understand all right, so what are the techniques that we have at our disposal or hyperbolic? Okay. Hyperbolic is kind of the best case scenario, so what are the tools or rather techniques that we'll be using? So one is the Beswina-Finn Hallway Finn. Okay, so let's look at this picture here. So what is Hallway flaring? Well, you take two lifts of this thing in Z. So you take lifts here, and so suppose this is identity. You have T square. So T represents this automorphism in the semi-direct product, right? And here you have W. So what are these lengths here? So then this length is simply this, and then you have TW, T inverse, so on and so forth. So T to the power n W by the relation that we have in the group is this. Right? We are actually, okay, so we are picking some lift here in this thing here. So this is a subgroup of odd. Okay. All right, so so you have this lift. So what does it mean to show flaring? We need to show that there is some exponent, some distance. You either move to the right or to the left, you get exponential divergence. Okay. So essentially, okay. So maybe I will write. So there exists some n such that for all maybe. So there is some threshold here. So you have to cross the threshold. Then you have 2 times okay. So this is nothing to do, nothing special with this, F semi-direct product Z. Given any extent, short exact sequence like this, if you can show that picking any two geodesics, you have this flaring condition, then you have hyperbolicity, right? So that's the one for hyperbolicity, and the relative hyperbolicity tool is the MJ-Reeves combination theorem. Okay. This is to Mahan and Lawrence Reeves. So what we have to do here is first you have to identify parabolics. Okay, which satisfies certain conditions. Cone of copies of okay. Third one is, so if we call this, maybe let's call this F hat. So show hallway flaring. In F hat. So you have the electrocuted metric, you want to show the hallway flaring. And the fourth one is the cone bounded hallway strictly flaring condition. Which one? F hat. So, okay, I'll explain. So that's why I wrote this in parentheses here, right? So you know what if you know you have guessed what your parabolics are going to be, you take the intersection of those parabolics with F, right? And you'll get a collection of malnormal quasi-convex subgroups in F. You cone them off, you get a relatively hyperbolic space, right? So this is a two-step cone off process. First, you cone off here, then you show these two properties. Then it says that, okay, you can again do the semi-direct product coning off. Okay, so this is one of the, to use this, in order to use this result is one of the key reasons why we have this Q to be either Z or F2, because you need a tree of spaces structure, right? And Z or F2 is going to naturally give you a tree of spaces structure where your vertex and edge groups are going to be F hat, right? And the automorphism and the identity map are going to give you the edge maps. Okay. Now the thing is, okay, so let's carry on with this, and then I will tell you the technicalities of this once we do the construction. All right, so these are the two steps here, right? To show hyperbolicity, you need only the Hallway-Flaring condition, and this you need to show these four steps here. All right, so given, so tools to prove the flaring conditions. So what tools do we have to prove the flaring conditions? First is the train track maps, relative train track maps. Second one is the weak attraction theorem for attracting laminations. So these are the key technical tools that we have to work with these automorphisms, and we're going to use them to show the flaring conditions. Okay. All right. So let me give you a quick overview of why, how will we using these things, right? So Damani already defined what a train track map is for a fully reducible outer automorphism. We need relative train track maps because our automorphisms may not be fully reducible. Okay. So this is a homotopy equivalence. Base point free homotopy equivalence, which represents phi. So this is a kind of topological representative of phi, and it has certain properties, right? So because you are assuming that they need not be fully reducible, so there is possibly some invariant free factors here, right? So you have a filtration like this. Where each of this is invariant. Each filtration element is invariant. And you let this so you take the difference here and add the vertices, so you get what is called a strata. And so this HI essentially relates to what Damani described as transition matrix now. So you have to look at HI, take its edges, and form a transition matrix. Right? Take an edge, look at its image under F, compute the Perron-Frobenius eigenvalue. Right? So that way, you know that exponentially growing if it has Perron-Frobenius eigenvalue. So the idea is the same. You take f, right, and you apply it on each edge of hi, and in its image, you look at what are the edges of hi that are appearing, right? This may not be, it's not necessarily true that f of hi is hi, right? It goes down and then comes up again and things like that. So you keep that count. So you construct a transition matrix, see if it is exponentially growing. All right. So these are and it may not be exponentially growing if the eigenvalue is 1, or it even may be the zero matrix. So we don't care about those things. All right. Now, if HR exponentially growing, then corresponding to this, there is a dynamical invariant called attracting lamination. So for each exponentially growing strata, you have something called the attracting lamination, right? And this is obtained, you can think of by taking where E is an edge okay. So this is it's a collection of infinite lines by infinite lines, right, with some properties, and essentially this is what is going to help us prove the flaring conditions. Okay, so now for each attracting lamination, what you have is attracting neighborhood. This neighborhood contains the entire lamination and has the property that and every conjugacy class which is in this open neighborhood, is in the limit, it will converge to this lamination, right? So it's just like you have an attracting fixed point and you have an open set, everything in the open set simply converges under taking limits here, okay? So what is the weak attraction theorem? This theorem is kind of the key here to get the bound on the exponents. Okay, maybe I write it here. So this first appeared in Bestina, Handel, and then Mosher and Handel and Mosher. I think this is 21. This is the memoirs paper. So they kind of expanded the treatment for this. This is a huge thing here, but anyway, the idea here is that given lambda r plus, right, and some attracting neighborhood, there exists n such that for any conjugacy class, let me just call it alpha, right? Okay, so we are not going to distinguish. Okay, so because we have a base point free homotopy equivalence there, you take immersed loops in G. They correspond directly to conjugacy classes in F. Right. So we are not going to distinguish between the conjugacy classes and the loops there. Just treat it like this. Circuit. A circuit is an immersed loop in G. One of the three things happens. At least one. Let me write it there. One is that phi to the power so this you take, so it gets attracted to this lamination. Right? This exponent is enough, right? Or so I'll explain this in a minute. So you have an attracting lamination here. So think of this as a stable lamination on a surface. Corresponding to this, you have an unstable lamination, right? Which is an attracting lamination of phi inverse. And this is an attracting neighborhood for, so this is neighborhood phi inverse. Right? Alpha has to kind of cross HR maybe, or it doesn't, even it doesn't. The third case is when it doesn't. So alpha is carried by non-attracting subgroup system of lambda plus r. So I have not defined this, but I will in a minute. So one of the three things happens. Either alpha is carried by this non-attracting subgroup system, or it is sitting inside the repelling neighborhood, or the nth iterate puts it inside the attracting neighborhood. Right? So just a bit of intuition of these two things. What does it mean here? Well, if it sits inside the let's call this a repelling neighborhood here, right? That means what? That means it, because this is a neighborhood of lambda r minus, for phi inverse, there are long illegal paths, right? And you have to really iterate this a lot to make it fall in this thing here. Right? If it does not have such long illegal paths, then it quickly comes to this attracting neighborhood. Okay, so what is this non-attracting subgroup system? Right? So this is a collection, finite collection of finitely generated subgroups of conjugacy classes. So you want to write this as with the following properties. One is that if Kj intersection W Ki is non-empty, non-identity, then I equals to J and W is in K. This is called a malnormal collection, right? So you pick any two groups, you just translate it a little bit at the level of the boundary, we always remain disjoint, right? 2 is every conjugacy class alpha carried by this K, then alpha does not limit, so phi to the power does not converge to lambda plus r. Okay. And third property is that if alpha is not carried by K, then phi to the power alpha converges to alpha. Right? So this is the duality here. If you are not carried by this, you will converge. If you are carried by this, you will not converge. Okay. Now, converge to a lamination is equivalent to saying that your circuit or your conjugacy class actually grows exponentially. Okay, under iteration. Now, so our yeah. No, this is just alpha conjugacy class. Okay, but a lamination carried by a subgroup means if you lift to the universal cover, the endpoints of that should not be lying in the endpoints of some conjugate of these subgroups. Okay. Now, so claim is that F semi-direct product phi is hyperbolic relative to this collection here. Ki semi-direct product, let's call it phi I, where phi I in OT is a lift which preserves Ki. Okay, this is the claim here, and as you can see that this kind of the guess is you have to use this weak attraction theorem and this thing here carefully to get this thing. All right. Yeah. No, his was more specific. So, okay, I will tell you. So these ones, right, the ones that he had, restriction to this was polynomially growing. These need not be. But the point is there is an induction process, because if you are exponentially growing here, you apply the same technique over and over again, you will end up with the groups that Francois had. All right. So what is the key thing here? So I have told you what these my parabolics are, right? So these are my parabolics. So I'm going to collect, that's what I put that thing in parentheses. I'm going to look at this collection here. Right? Let's say this, whatever I have here. I'm going to cone off cosets of Ki's in F, and you get F hat, right, with this metric here. Let's call this the electrocuted matrix. Why is this? Well, it is because of the malnormal property that you had here, first property, and that because these are finitely generated subgroups, so infinite index subgroups, so you get quasi-convexity, right? And you're coning off a hyperbolic group with respect to a collection of quasi-convex malnormal subgroups. So this is relatively hyperbolic. Okay. And we have to show the relative hyperbolicity here by showing this flaring conditions. Okay. So how do we do that? So the important, okay, so the thing is that all these things are actually constructed. Once you know how to construct the train track map, you can actually collect all this data. Now, how to show flaring? Okay. Well, for this, what we need to do is we have to relate that electrocuted metric to some kind of a length that we can compute on the graph. Okay, so these are the kind of two main ideas. One is to identify the parabolics. Second is how to count this electrocuted metric. Okay, the rest, once you have these two, you can easily show the flaring conditions. Okay, so the counting. Right. So you have this. Right. What you do is you consider the Stalling subgraph. Okay. So what Stalling subgraph is an immersion. So this is an immersion of a finite graph. This is finite graph. Okay, with components. These are all core graphs, so there are no valence 1 vertices. A1, AP, right? Such that the induced map so Ki is conjugate to the image. So you look at the image here, right? In F, and Ki should be conjugate Kj. Kj should be conjugate to this thing here, right? So this is the Stalling subgraph. All right. So now you have the Stalling subgraph. Let me tell you how to compute the length here. So beta be any immersed path. So you take any immersed path, what you're going to do is you're going to decompose beta in this formula. These are all finite segments, finite, right? You write a decomposition so that this is a path that does not lift to GK, and maybe let me write beta 2. This is a path leads to GK. These are the paths that we are going to ignore. If you are lifting to GK, essentially the idea is you are being coned off, right? And now let's look at beta 1. If it does not lead to GK, you write it as a decomposition like this. Okay, and what are these? This is a leaf segment, so subpath of some leaf of an attracting lamination of lambda. Let's just write of lambda. Right, so every element of lambda plus r is called a leaf because it's a line, and you want this to be a subpath. So this is not a leaf segment. Right? All right. And so the right. So what you want to do is you want to write this one second. So beta I does not lift to GK, right? And you write L so beta 1 was a leaf segment. This is equal to sigma of this beta y is sufficiently long leaf segment. So it's a finite subpath in a leaf, and it has to be sufficiently long. So this sufficiently long is actually quantified in terms of the bounded cancellation constant and stuff. But you calculate this, and then you let the legality of beta to be equal to maximum over all decompositions. All such decompositions of this ratio. What is the ratio? This is L star legality of beta of this. So you take all possible decompositions, there are finitely many, take the maximum one, right? And you let Lk of beta equals to L star k of beta for the max decomposition. The crucial lemma here is that if alpha is a circuit in G not carried by K, then you have 1 over J, then, okay, just write it. So this number here actually tracks the electrocuted metric, okay? And you can actually do this thing in the graph. Okay, so this is the length of the conjugacy class. It means you take the shortest representative of the conjugacy class and compute its length in the electrocuted metric, okay? And basically that's it. From here, what you get is you start proving things, so you will get what is the conjugacy flaring, and so you'll get conjugacy flaring and then cone bounded Halley flaring and stuff. Okay, so so the cone bounded Halley flaring, I can get to it. Essentially, you know, you keep working with this. what it essentially says is, if you pick some lift, say phi I, let's say phi 1 equals to k1, and say ki equals to xi inverse ki xi. So it's going to fix k1, send ki to another conjugate. So the cone bounded Holloway flaring amounts to showing that these conjugators will grow exponentially in the electrocuted matrix. And once you have these two things, you'll get the relative hyperbolicity in the free bicyclic case. Right? Yeah, okay, let's stop here.
Questions?
Yeah. What is the statement for free by free? Okay, so the free by free thing that we have here, that we managed to prove, is that you need to have collection of this, like I described the non-iterating subgroup system. We define what is something called an admissible subgroup system. It has the same properties, but it need not be associated to a particular lamination, right? But it will have the list of all the properties that we listed. And if two automorphisms end up having the same admissible, so same kind of parabolics. So there is a thing like that K, so you have K1, and these outer automorphisms actually preserve the conjugacy class of each of them, these KIs. Then you can construct F2 like this. Like this, plus laminations not carried by K are disjoint, pairwise disjoint. So this has a bunch of attracting laminations, repelling laminations, and you have this, what we are saying, this subgroup parabolic system. You don't want your laminations, you want to have some laminations outside of those parabolics, right? Not carried by these KIs, and you want them to be pairwise disjoint. Then you can construct this. Okay, this is actually a necessary condition. If you violate this, you never get relative hyperbolicity. So this is essentially, yeah. So anyway, so yes, if there are no parabolics, then you just assume that the set of attracting and repelling laminations are pairwise disjoint, and that's enough. You'll get a free by free hyperbolic extension. This is actually the most general statement you can have for free by free case in the present, using the present tools that are available. This is similar to the Schottky construction by Farber and Moshe in the mapping class groups case. You have pseudo-Anosov with independent laminations, you'll get a free by free, surface by free hyperbolic group. Sort of. So the statement is that if you have a free by free, if you have a free by free hyperbolic extension, right? So this is hyperbolic relative to this Ki semi-direct product. You pick some lifts. You pick some lifts which will preserve these Ki's. Right? If you have admissible subgroup system, this is true. If this is true, you can immediately see that, okay, you will of course get an admissible subgroup system by collecting these Ki's. So it's an if and only if in that sense. So admissible subgroup system plus pairwise disjoint laminations implies free by free relatively hyperbolic with this structure. We call this the cast preserving structure, essentially inspired by the surface theory. The converse is of course true. So it's a if and only if. And for the free by free hyperbolic case, again, same thing. Lamination disjoint implies free by free hyperbolic. Converse is of course true by, few years back I proved that given single toroidal automorphism, the ending lamination set is actually the Beswin-Affin handle lamination, the attracting lamination, plus some finitely many lines. So now if you look at Mahan's earlier papers where he developed this ending, for extension group, the Cannon-Thurston maps, given two distinct points in the boundary, your ending laminations must be disjoint. So that is a necessary condition, laminations being disjoint. Absolutely, yes. Yeah. So in this case, you may have some laminations to be same, but it must be trapped inside this parabolic system.
So, like if you're not disjoint, you have an accidental torus.
Yeah.
That always happens.
Which one?
So the laminations are not disjoint.
Yes, right. Yeah.
So is having disjoint laminations equivalent to being atoroidal?
In disjoint laminations being atoroidal, no. You may fix some rank 1 free factor, right? And you can have disjoint lamination. So take two fully reducible independent automorphisms and which are disjoint, right? And you attach a loop which you fix in both.
What if it was fully reducible?
Fully reducible, no. I mean, you take the case of a surface with a boundary, take two distinct pseudo-anosovs. So you're going to end up fixing that boundary component. So you will not be atoroidal. So disjointness of laminations and atoroidality are not really that deeply connected. Yeah. These both have to be atoroidal to start with, right? Because that's a necessary condition. You cannot fix something and you have a z plus z and expect the extension group to be relatively hyperbolic. So the things that we have not been able to show here is the case, for example, take this to be hyperbolic, fully reducible, relative geometric fully reducible. So pseudo-anosov on a surface with one boundary component. You can easily, raise to high powers, get a free by free group. We don't know whether that will be relatively hyperbolic with respect to the z plus z subgroup or not. In fact, not only in that case, if there is no admissible system preserved, whether we have relatively hyperbolic, we don't have any counter examples or examples. That's
Any more questions? Okay, let's thank the speaker again.
Thank you.